Hi folks, let's take a little bit of time here just to talk about some of the basic ideas that we can analyze with our spreadsheets here. So I've got some data in here, and this is just, I think it's data about flus in early reporting in like the early 1900s, probably in America, of just how many flus were diagnosed and then how many people died of them. So we're going to look at kind of what is it that we can do to kind of analyze these and what can we kind of figure out about them. So the first thing we're going to do is just make a basic scatter plot. So if we go to Insert, we go to Chart. If you click on that, it'll guess for you, but if it didn't work, what you'll want to do is come over to Charts over here and choose a scatter chart. So let me scroll down, make sure you can see. If you look about halfway down, you'll find the scatter chart. Click that. Now we want to make sure it's plotting the right things. It makes sense to us that diagnoses would be our explanatory variable, and deaths would be our predicted variable. So we're going to put diagnosis on our X. We're going to put deaths on our Y. And because I chose to include the diagnosis and death, I will use row 1 as headers. Now, once I've got this chart, I can do some work here. If I come to my series, I can go down, and I think it might just barely be able to see it. I can click trend line. And then I want to make sure that it's linear because that's what we're dealing with. Now you can't see it because it's behind my camera here, but just below that you'll see label, and I can say use equation. That will give me my equation up here. And I can also click show r squared, and that will give me my coefficient of determination. So now that we've got that, that's actually most of what we learned about in this unit. So in theory, we're kind of, good to go, so to speak. But let's do some more of that by hand, because you may not want to have to graph all this, or you may want to get better values than just 3 decimal places and 2 decimal places. So let's run through some of that here. So let's close that back, come back over. And there we go. Okay. So first, if you remember from our equations, we're going to need a handful of values here. So we're going to need the mean. So we'll just go back in and put that in like we've done before. Average, and it's picked what I want, so great. And then standard deviation equals standard deviation. Again, this is nothing new. That's auto-selecting, great. Average. And C2 to 24, great. And standard deviation, C2 to 24, great. Okay, so now what we want to do is start looking at some more specific calculations. Those will come in useful later, I'm just putting them in now. So now for correlation, there is a function in Google Sheets to do this. So I'm going to type CORREL, and you'll see it says the Pearson product moment correlation coefficient. That's the way that we've learned it. There's other correlation coefficients, but this is the one that we've learned and that we'll use. Now, this is a bit tricky. For all of these, you need to pay attention to what they tell you. So they say correlation, data Y, comma, data X. So we're used to having X in our first column, Y in our second. That's fine, we just need to make sure that we choose our Y values, which again is our predicted variable. Then it's going to say comma, data X. Now I'm going to choose my X values. And then I can hit enter. We don't want those autofills. And you'll see it gives me my correlation right here. There's not... the correlation calculation is kind of messy, so we're not going to worry about calculating that here. But I'll show you for some of these the equation we could use if you wanted to calculate it manually. Now, for slope of the least squares regression, there's also one for that. So if we type slope, look, you'll see that it says slope of a line from a linear regression of data. That's what we have. So slope, again, we choose data y first, comma, data x. And again, these are just for linear regression. So if you're doing some other sort of regression, this won't work. And these are just for least squares linear regressions, which is what we're doing in this unit, but just know for the future that may not work. Type it in, and you'll notice we get the same values we did on the chart, but more precise here, 0.60762, blah, 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 0.608. Intercept is going to be equals, as you might guess, intercept, y-intercept of a derived line via linear regression. Excuse me. So again, in all of these cases, they want the y values first, then the x values, and we get our least squares regression. And then coefficient of determination, or r squared, that's going to be, this one's a little different, RSQ, the square of the correlation coefficient, which is what r actually is. If we type that again, put in our y values, put in our x values, and we get, you'll notice 0.954, which matches our 954 here, but again, it will give us functionally our many, many more digits. This one, again, we won't worry about calculating. Now, if you remember from your notes, or if you go back and check, we know that the slope, of the least squares regression is also equal to, oops, sorry, I messed up my notes over here, so I'll put that back. We know that it's also equal to the correlation coefficient times the standard deviation of the y value divided by the standard deviation of the x value. You can go back and check in your notes, but what we'll see here is, in fact, that's what happened here. And that's how they calculated in this function. It's just they've got that happening behind the scenes. The intercept is a little bit trickier, but it involves using what we call point slope form. You may have learned this in math, but it looks like this. So if you write the equation y minus a known y value and have that equal to the slope times x minus a known x value, so I just pick a point that I know is on my line and I plug that point in for x val and y val, then this gives me the equation for that line. If I rearrange that, I have y equals bx minus bx val plus y val. So again, the x val, and let me put this as a times in there, oops, times. The x val is just a value that I know from the graph. The y val is just a y value that I know from the graph. And if we remember, again, check your notes if you forgot, the mean of x prime and the mean of x and the mean of y will be on our least squares regression. So I can come up here and I can say equals, the y-intercept is going to be negative b val x val plus y val. And if that sort of goes over your head, you don't really need to know this, but it's useful just to kind of have it if you're curious. If it flies over your head and you just want to use intercept, that's also fine. So we are going to take the correlation, or the slope, we're going to multiply it by our known x value, which is our average from our x. And then we're going to add our y average. But remember, it needs to be negative b val. So I'm going to put a negative sign on here. And if we enter it, we see that we do, in fact, get the same number. Again, these are just showing you and reminding you how those calculations are done. so you know that what's going on in the background. Okay, next we want to create a residual plot here. And so in order to create a residual plot, we need to have our predicted y values. So the predicted y value is going to be what we get if we plug it into our equation. So that's going to equal the diagnosis number, our x value, multiplied by our slope plus our intercept. And that's just basic y equals a plus bx. So if you prefer, I'll even write it in the form that we have in the book. A plus b times x. So we do that, and we're going to copy that and paste it all the way down. Because we need to come back up here, and we need to make these always refer to H3 and always refer to, not B2, always refer to H4. Because again, if I don't have those, it'll just move down respectively. So you'll see here, H4 and H5, etc. So now when I copy and paste, we should get all of our predicted y values. So if we want to make the residual plot, we need to find the residual, which is the difference between the predicted value and the actual value. And it's always taking the actual value and subtracting the predicted value. So we're going to come to our diagnosis, our actual value, and then we're going to subtract our predicted value. Oh, whoops, that's the problem. We go to our actual value and we subtract our predicted value. And if I grab those and paste down, we're okay because we're always looking at the two numbers left to it. So now I can create my residual plot by inserting a chart. And you'll notice it actually came in here and it figured out what I wanted to do based on what I had already done. But if that had not been correct, we can come over here and double check. If we click on this, we're looking at our data range, B1 to B24 and E1 to E24. So we want diagnoses versus residuals, because again, we always want our x-axes to match up. And then we've got diagnoses, we've got residuals. We don't want to put a line of best fit on here because that doesn't make sense. But what we see here is basically, yes, as we go out, we see we get more spread. So that means that, you know, early on, there was a pretty tight correlation respectively, but as time goes on, that gets less and less accurate. And we can see kind of how these match up. Like we see these 3 points that are above match with these 3 points here, and it kind of all sort of matches up. So a residual plot isn't necessarily super useful for doing anything other than just making sure that this line is a good fit. It's another way, in addition to the r squared, it's actually the more basic, faster form than r squared if you didn't have a computer to get a feel for it. But like I said, we do also are able to say that as we get farther up, this becomes less precise. So we wouldn't necessarily want to extrapolate this out to a large number because we would expect a fair bit of error. And the last thing I'll just mention, the standard deviation of our residual tells us that any given prediction, like if we wanted to predict the number of deaths from, say, a diagnosis of, say, 2,300 here, where we don't have anything, we'd expect to be off by about this much. And so if we weren't okay with this amount of inaccuracy, we wouldn't want to use this linear regression to make predictions. So that's the basic idea here. Let me know what questions you have, but otherwise you can jump into the rest of your work.